and welcome to the podcast of Loughborough University's Institute of Advanced Studies, a podcast where our international fellows discuss the most pressing issues of today that we're all facing and share their exciting research ideas. We hope you enjoyed today's talk. Thank you for tuning in.
Yeah, thank you for coming. And before the seminar, I'd like to introduce Professor Yan Yin to you. And Professor Yan Yin received her degree from Yamaguchi University in 2003 in Japan. And since then, she joined the Tianjin University and has been a faculty member in State Laboratory of Engines. At the same time, she also served as the Deputy Director of the National Energy Storage and Innovation Center in Tianjin University. And her research focuses on polymer electrolyte fuel cells, water electrolyzers for green hydrogen production and utilization. In that area, she has published over 150 papers in high reputation journals such as Nature Energy, Energy Environmental Science, etc. And these publications have gained over 10,000 citations. And therefore, she has been listed as one of the top 2% scientists in her area across worldwide. And on a personal note, Professor Yan Yin was also my personal tutor when I was an undergraduate in Tianjin University. And she really gave me a lot of impact on my academic development. Actually, I was motivated by the conversation with her and to pursue my PhD. Yes, okay. So please join me in welcoming Professor Yan Yin.
Thank you very much for Jason's kind introduction. Actually, my English is just so. So if there are some problems in communication, Jason will help me. Thank you in advance. Okay, this is the first time for me to come to England. And I'm impressed by today's wind. Just now, I said probably the wind brings me from China to Loughborough University. Okay, I'm glad to think about this kind of things because my name Yan Yin in Chinese in Yan. There's also you can see 春天来了，引来了燕子. So there are some relationship between my name and the spring. Spring is coming means my name. So I'm very glad to share this information. Okay. My topic today is concentrated on the design strategy for polymer electrolyte membranes in a hydrogen energy conversion system, including both fuel cells and water electrolyzers. First of all, let me say a little bit about State Laboratory of Engine and the National Industry Education Platform for Energy Storage. I am a professor in SKLE and also do some work in NIPOS. SKLE was established about 40 years ago in China. So the main task for SKLE is mainly about traditional engines, including diesel, gasoline devices for marine, space flight, or locomotive, etc. And the MEAs was just established about 4 years ago. It's a very new institute. And the main one of the main research direction in these two institutes include hydrogen-related works. For example, fuel cell and electrolyzer related work mainly includes non-precious metal catalyst or structure design and CFD model modeling work or flow channel design to optimize fuel utilization in both fuel cell and water electrolyzers. And specifically, the materials for membrane electrode assembly being used in both fuel cell or electrolyzer, including the materials research. For example, anion exchange membrane, M, and proton exchange membrane, so-called PEM. So these kind of materials are one of the key directions in SQLE and NIPOS. Okay, and this slide shows the team member in our group, which Professor Michael Gower, he is English, and he has been working in Tianjin University for more than 12 years and is our leader in our materials group. So HEMLab means our name of our group, Hydrogen Electric Energy Conversion Materials Lab, so abbreviated as HEMLab. And this is me, okay, and Professor Junfeng and Lian Qin, and the background of our team member, the teachers, compensate to each other perfectly, because we have a membrane research, we have a catalyst, we have a membrane, we have MEA fabrication. So from material science to engineering work, yeah, all combined to each other. So the target of our group is mainly to pioneer the development of key materials for the next generation hydrogen electric energy conversion, especially from the viewpoint of materials research, including the electrolyte membranes with ultra high conductivity on the related catalyst. For example, the interface between membrane, ionomer, and the catalyst. There's a triple phase boundary and the interface interactions. And the key point of our research group includes electrochemical reactions and the triple phase mass transfer problems. So our main research direction includes novel polymer design for high-ion transport, the contribution of the polymer architecture. And second is the smart direct structure design for efficient triple phase reaction. And this part is related not only to membrane, but also to catalyst and ionomers between the triple phase interaction. And the MEA design is an probably towards engineering, because MEA design should be based on the progress of membrane together with ionomer and catalyst. Okay, so let's go to some background and motivation of my research topic today. Because our mission, I think the world researchers have the same dream, that we are responsible to develop a clean, efficient, and green world, right? And we should focus on our research to develop a world with safety and friendly to our environment. So, and the fuel cell and the electrolyzer share the same dream with our task. And for example, when we use anion exchange membrane as one of the key material, because AEM, anion exchange membrane, both fuel cells and electrolyzers in alkaline environment can use non-precious metal as a catalyst, and then it can lower the total cost of the devices for both fuel cell and electrolyzers. In the left graph, you can see for the water electrolyzer, and the purpose is to produce hydrogen, pure hydrogen efficiently. And the middle diagram shows the M fuel cell using anion exchange membrane as a polyelectrolyte. And the goal is to have efficient power output and durable interface during the membrane and the catalyst. Okay, and for the different system, for either fuel cell or water electrolyzer, they share the same bottleneck, such as both systems needs reliable membrane and exchange membrane, and occasionally the catalyst researchers are trying their best to develop non-noble metal catalyst in an alkaline environment. Okay, here the key point, AEM membrane material and the anion exchange ionomer together with catalyst, they combine together to fabricate MEA. So correspondingly, the performance of the MEA is influenced by the three parts. Okay, and from now up to date, let's say something about the membrane. Membrane material, the traditional structure you can see on the top right. This shows naphthalene, naphthalene as a representative of proton exchange membrane, it has a perfect microphase separate structure, and as the probably only commercially available product for PEM, naphthalene has many advantages, such as 3 highs. One is high conductivity, high mechanical stability, and high electrochemical stability, right? But for naphthalene, although it has a good compatibility for ionomer together with membrane, and it has a good conductivity and chemical stable only under relatively low temperature, below 100 degrees C, because it has a relatively low glass transition temperature around 110. So when the temperature arises to near 100 degrees C, the membrane will become soft and they will lose the mechanical strength. And another important drawback for the naphthalene is that it will dehydrate at high temperature. That means its conductivity will decrease drastically at high temperature. So researchers have done many research to develop other polymer electrolyte membranes as alternative to naphthalene, mainly focusing on the hydrocarbon PEMs. However, for the hydrocarbon PEM development, it has potential for higher temperature for both PEM fuel cell and M fuel cell or water electrolyzers, especially when you use hydrocarbon not LQ type, had some benzene rings. It can have a good thermal stability, but we need to control the dehydration tendency. Also faces the same problem at temperatures a little bit high, over in the range of 90 degrees C to 120 degrees C. During this range, the water dehydrates easily. So we need to consider the same problem. And we need to develop cheaper, mechanically robust and tough as well as flexible membranes for hydrocarbon PEMs and AMs. And this slide just give an example, of PEM. But at present, for hydrocarbon PEMs, they also have some problems, such as the proton conductivity is quite low when the membrane has a similar ion exchange capacity, IEC, with naphthalene. Under the same IEC level, hydrocarbon-based PEMs usually have relatively lower conductivity compared to naphthalene. And the higher dimensional swelling at high IECs needed for fuel cells need to be considered. So the design, the strategy of the hydrocarbon PEM should be considered. Think about the dimension swelling and water uptake together with the conductivity coupled to each other, okay? And for some hydrocarbon PEMs, the custom ionomers have some problem compatibility. So at present, even for MEA using hydrocarbon-based polyelectrolyte membranes, naphthalene-like ionomers is still necessary because the compatibility is a problem. So the chemical stability, we should think about it all the time. Usually hydrocarbon-based PEMs have a not so good chemical stability compared with naphthalene. Okay, and during the last decades, there are basically two routes to synthesize the PEMs using a sulfonated polymer as an example. First, you can get the sulfonated polymer via direct sulfonation process, which is very simple. And you need to think that this the first route via direct sulfonation usually have low sulfonation degree. That means we cannot control the sulfonation degree accurately. And sometimes if you make a severe sulfonation, you may suffering from the degradation of polymer main chain. That this is the first route. And another method is to synthesize sulfonate polymer from monomer. You can since you can get sulfonated monomer first, then you can get sulfonated polymer via copolymerization. This kind of method can control the sulfonation degree accurately. You can design the IEC value, and then you can get a high molecular weight polymer. But this method is usually complicated, and sometimes you cannot get a high molecular weight polymer. So both methods have its advantages and disadvantages, okay? And about 20 years ago, when I am in Yamaguchi University for my PhD degree and postdoc, I did a lot of research on hydrocarbon-based PEM, proton exchange membrane, including sulfonated polyester ketone and sulfonated polyphenolene sulfide, and sulfonated polysulfone and sulfonated polyimide, etc. And you can see all the hydrocarbon-based PEMs shown in this slide is called main chain type. That is, the sulfonated acid group is bonded to the polymer backbone, directly to the polymer backbone. We call this main chain type polymers, polyelectrolytes. Usually, if this kind of main chain type polymers have some microphase separate structure as shown like that, and the black part means the hydrophilic domain, and the gray part means the polymer backbone. And this kind of microphase separated structure is crucial to determine the conducting performance. Okay. Another type is called side chain type, and the naphthalene is one example of side chain type. And for hydrocarbon-based PEMs, you can see linear or cross-linked sulfonated polystyrene and polybenzimidazole-based side chain type, and as well as sulfonated polyimide. And side chain type, you can see from the name that sulfonate acid group bonded to the polymer side chain as a terminal group. Okay, and this kind of polymer electrolyte usually have a better microphase separated structure as shown in the slide. You can see the dark part, the hydrophilic domain connected to each other, right? And this kind of structure design resembles naphthalene much better than the main chain type. So, and about 20 years ago, the research for anion exchange membrane, probably the first study for M fuel cell started from John Wackel's group. John Wackel's group, and his group reported the first study about radiation grafted membrane for M fuel cells. And another group, Zhuang, China's researcher, Zhuang's group reported the first non-noble catalyst research for anion exchange membrane fuel cells. And later on, ever since 2010, researchers developed many kinds of polymer electrolytes as anion exchange membranes, and the main target during this period is to improve the ionic conductivity for anion exchange membranes. And very recently, about 10 years ago, the target for M fuel cell is mainly focusing on the alkaline stability. So this is a developed map of the anion exchange membranes. So also I have done some research for fuel cell or water electrolyzer for almost 20 years. So I always ask myself from my polymer electrolyte material perspective that many questions need to be synced. Some key challenges such as how to maintain sufficient ionic conductivity and do water retention at elevated temperature, because this is a common problem for naphthalene, for many other membranes. The same situation is that at higher temperature, they will dehydrate and the ion conductivity decreased drastically. So this is the main challenge. And next, how to decoupling high ion conductivity from poor dimensional stability, because usually if we increase the IEC value, we can get high conductivity, but at the same time, the membrane will have a higher water uptake which results in a severe membrane swelling problem. Coupled, how to decouple this situation is another challenge. Are there any ways to improve conduction? Does free volume play a role? And specifically, can ionic channels be aligned in a beneficial way? And this question, probably I started to ask myself more than 10 years ago, just like a dream. And the dream lasted for more than 10 years for me, because it is not easy. And how can I improve chemical and oxidative stability for both amps and PAMs is another problem. So I cannot solve all of the questions. I can just focus on some of them. Here comes the advanced ion exchange membranes and the design strategies in my group, okay? Yeah, just as said before, many researchers have done large amount of work towards developing novel structure for hydrocarbon-based polymers, and they can synthesize many kinds of structure via branching, co-polymerization, and other methods. And for the case of hydrocarbon polyelectrolytes, the triple block copolymer have some advantages. Microphase separated morphology can improve conductivity to some degree. We can control the structure, and somewhat this kind of morphology, it have a hydrophilic domain and hydrophobic moiety, and the separation, microphase separation structure somewhat mitigates the dimensional swelling sometimes. And the ion conduction path is usually tortuous, probably have the conducting the ion transportation channel have some long distance, will decrease the efficiency of ion transport. And another problem is the ion conduction paths may also not be connected. If the hydrophilic domain is isolated like an island, the ion conducting performance is low, although the microphase separate structure works to some degree. So what if we could make shorter pathway highly conducting channels? Is it possible? And can we align them through plane? Through plane means across the membrane thickness direction. It's not easy. And embed them in the non-swelling matrix or decouple dimensional swelling and conductivity. So here comes our concept, and our work is mainly focused on the structure design and the performance evaluation. As here shown, the Nathan's microstructure have a perfect microphase separation morphology, and this kind of product has high dependence of conductivity on humidity. That means if we increase temperature, the conductivity decreases drastically. So this is a problem. So how can we regulate the polymer structure to mitigate this kind of situation? The construction of ion conducting channels lies in the large amount of polymerization and polymer chemical composition together with the structure optimization. So large amount of research lies in this diagram. And the hydrophilic domains, you can regulate to concentrate the hydrophilic domains together to better transport ions, but it's not easy, okay? And the concept is that can we construct this kind of a structure that highly induced channels for ion conduction? Is it possible? So after more than 10 years of hard work, I mean the dream, realize the dream to reality needs a long time, many years. So we finally got this kind of structure. This is a microscope using a high resolution TAM. Exactly, we can realize this kind of structure. You can see the dark part like a channel-like, right? And it can provide some highway transportation for ion conduction. However, it is not easy to realize this structure. So how can we do this? We sometimes If you cannot solve a problem via chemistry, then try physics. If not either, then try mathematics. Sometimes probably you need literature or philosophy to solve some natural science problem. So that's my understanding. So the magnetic field assisted casting helped to develop a highly induced proton conducting channels. If we select some coordinate group, very easy to boost ion conduction. But this kind of polymer, highly conducting polymer, is usually water soluble or not stable. So we first synthesize some highly conducted polymer and embed them to a matrix. The matrix probably is not proton conductive, but it can provide the stability, right? And the dimensional stability. And we mixed this and put it in a high strong magnetic field, then cast it into membrane. Then we can get a stable proton conducting material with highly conducted ion channel across membrane thickness. We call it through pollen direction conducting polymer. Okay, just like this shown. You can see this is a polymer matrix. We can use a very cheap plastic such as polysulfone, and we can use the coordinate material highly proton conducting. For example, heteropolyacid. It is unstable, but we can mix the highly conducting coordinates into the polymer matrix and put it in the magnetic field environment. So we did get improvement in fuel cell performance using this kind of. And how, if we do the same way for anion exchange membrane design, we can also get some improvements. Here you can see we use the magnetic field induced mixed valence ferrocenium series. Ferrocenium anion exchange membranes, aligning the conductivity and the stability for high performance fuel cells. Here you can also see in the right diagram, you see clearly of the highly induced channels in the 10 micro images for anion exchange membrane. Using this kind of method, you need to consider that the ion conduction coordinates should be ferromagnetic. It should be sensitive to magnetism field. Okay. Okay, we can get the through plane conductivity of anion exchange membrane around 160 millisiemens per centimeter at a relatively high temperature, such as 95 degrees C. And we can also get a good conductivity stability until around 4,000 hours. And we can have a relatively good max power density, peak power density, because the membrane is relatively thick. If it can be thinner, probably the peak power density can be increased. Okay, and here the right bottom diagram shows the stability of the membrane and exchange membrane. And we published this serious work in the Nature Communications, Nature Energy, and Energy and Environmental Science, and about 5 or 6 years ago. But the work begins more than 10 years ago. Okay. So here is the second part of the membrane design. Randomly branched polyarropyridine-based anion exchange membranes, because the terphenol, this kind of a polymer, has advantages of high stability in alkaline environment and high hydroxide conducting performance. But this kind of membrane has a drawback, is swelling, because the water uptake is pretty high and the dimensional stability is poor. So in order to solve the water management in piperidine-based anion exchange membranes, researchers can use copolymerization or cross-linking. Via copolymerization, you can get a good cell output, and the cell durability is not high, it's not good enough. And during cross-linking, you can get a good cell durability. And in our group, we use a branching agent such as TPB, triphenylbenzene. We use this as branching reagent to adjust the branching degree of the piperidine-based membranes. Okay, through random copolymerization using the TPB branching, we can investigate the water absorption behavior or water uptake to solve if we can improve the water stability for the PTP-based membranes. When we push the membrane into both liquid or water vapor, we can see the result that slightly branched PTP-based membrane has much lower water uptake compared with the precursor PTP-based membranes. However, the conducting performance is still good. You can see, if you look at the top right diagram, the conductivity, the branched with 0.5% branched sample, you can get obviously improved conductivity. If you look at the mechanical property for the slightly branched membrane, you can see it has a good mechanical property as well as the flexibility. This means that we can get a tough, flexible membrane with high conducting performance using slightly branching method. And here, if you look at the fuel cell performance using a pure hydrogen and oxygen, and with 100 kilopascal back pressure, you can get a good fuel cell performance for 0.5% branching sample. And for example, at 100 degrees C, a relatively high temperature for M fuel cells, usually you can only get the performance below 80 degrees C, right? And the peak pulp density reaches 2 watt per square centimeter. And as to the stability, we can get at least 200 hours stable operation using this kind of membrane at 100 degrees C. We published this work in June in 2024. Okay, another part for the polyelectrolyte design is towards grafted, radiation grafted ends. We are inspired from the nature situation that, as shown in this slide, we can design resembles leaves that we can have a hydrophilic domain. We can artificially design the hydrophilic domain and make the polymer surface have some micro nano structure. Okay, so that's shown. We use ETFE as the basic matrix of the polymer membrane, and using some roller embossing, this kind of method to make the surface rough, not very roughly. Then we can have some irradiation effect to get the ETFE micro nano. We call this MN, ETFE MN membrane sample. So with this method, the biomimetic microstructure is promising. We can use this method to produce membranes, anion exchange membranes with high conducting performance. And we did some modulation work using molecular dynamics simulation for our membrane and for a commercially available anion exchange membrane such as sustaining. And from the calculation, we can see that for our radiated membrane, we can get a more connected hydrophilic domain, more concentrated hydrophilic domain for better ion conduction compared with the commercially available membrane. And the bottom shows the atomic force microscope shown like that. You can see if we look at the conducting performance and as well as the dimensional stability, we can get our work, we can get as high as more than 300 millisiemens per centimeter, a pretty high anion conductivity. And we can also have about Swelling ratio is relatively low compared with some commercial samples shown in the plot. And here I just paid more attention for the mechanical properties for ETFE because ETFE series membrane is flexible and sometimes the mechanical property has some problem. So if we compare our normal membrane with the commercially available sustaining, we can see that the mechanical strength is not bad. Okay, and we can produce a membrane laboratory made little bit scale. You can see it's to students. It can have 5 meters long and about 50 centimeter wide. Okay, this work is here. The stress strain plot is shown like that. And another question is about the ionomers. This kind of design for anion exchange membrane using radiation grafting method, we can prepare both membrane and ionomer with exactly the same chemical composition, right? And this membrane has better catalyst adhesion even with an ultra-low catalyst loading as shown in the top right. You can see the short-term stability compose the membrane and the ionomer together with the catalyst in our lab. This is before the stability test, and the right diagram shows after 1 hour test. You can compare the performance using our novel membrane MN and with ETFE, and as a reference, you can see the membrane has a good performance in durability. Here, the long-term durability using the radiation grafted M as ionomer, you can get a stable M water electrolyzer. Next part is focusing on the ionomer research, because ionomer paid more attention on the triple phase boundary triple phase interface between membrane and the catalyst, especially when you fabricate MEA. And we did some research on the microstructure difference between the polymer electrolyte. We use QAPPT, this kind of structure, and the only difference is the matter or para position. They are twins, they are analogs, right? And we investigate when we use this twin as the ionomer, how does it influence the catalyst layer evolution during the cycles of humidity or temperature. Okay, so here from some molecular design, we can have some information that when they do the AST test using the conditions from room temperature, low humidity to 80 degrees C and 95 relative humidity, and run this cycle many times. We look at the difference of the ionomer evolution behavior. Can see using metal position ionomer sample, the volume increase about 70%. But for parallel position based one can get a larger volume increase. This means if we use contorted, such as metal position QAPPT, it is contorted the structure, and the parallel is rather like a linear type, right? Linear parallel P QAPPT can reduce the total one metal position can reduce swelling to some degree. Okay, so if we look at the MEA, therefrom, using this twine ionomer, we can see after the AST test, for example, the dynamic relative humidity cycling causes the ionomer migration, the plus crack growth when used to fabricate catalyst layer, can lead to fast performance decay. And we published this in the Journal of Material Chemistry as a cover paper because we proved the microstructure did influence the ionomer migration behavior in the catalyst layer, and for both fuel cell or water electrolyzer in the MEA. Okay, and this slide shows a comparison. We bought several types of commercially available ionomer and did a serious study when the different, all of the ionomer shown here are commercially available, but we want to know what is the difference between these products as ionomers in the catalyst layer. We see when you coupled rigid tryptophan, some rigid structure together with bisphenol fluorine, you can get increased free volume in the microstructure. And also, if we put hydrophilic groups such as phenolic hydroxyls, we can create hydrogen bond networks, which is favorable for water absorption, for hydrogen absorption. And the highly hydrophilic anion exchange ionomers for microphase water control in water electrolyzer, we can see that the H bonds strengthen the binding of water to the polymer. This is this is a phenomenon we observed in our experiment. If we look at the water uptake values, we can see if we put the flexible group into the ionomer structure, we can get much better water uptake and water diffusion coefficients, such as for the new ionomer materials, we can get water uptake as high as 300%, much higher than the commercially Piper ion A40 sample, which has only about 30%. And correspondingly, we get faster water diffusion coefficients 2 times that of commercially available ionomer. And this slide shows the our group. We comparatively you can see the Piper ion, sustaining, and the Fullman. All these are commercially available ionomers. The flexible ionomers are beneficial for to get a better microstructure. So we can introduce flexible groups into the backbone to optimize the catalyst microstructure. The next part is something about the catalyst and design, especially for catalyst layer or MEA fabrication. And for the catalyst study, there are several points need to be considered. First is the activity. Second is stability. Yeah, if you can combine the stability and the activity, you can do a good work, because usually these two properties contradict to each other, right? So the first, we aimed at improving the activity of the catalyst. And here is the nickel iron alloy research, because for some catalyst, the microstructure is just like a solid bond. That means you can only realize the catalyst performance on the surface, but some atoms is inside the particle. So you need to pick up the dormant atoms inside the catalyst particle. So here we introduced molybdenum to achieve porous of the catalyst particle. Then we can have a higher surface activity. This is our concept of the molybdenum leaching to fabricate a porous frame of the catalyst. Then we can get a better performance. And if we look at the stability, you can see that for some high active catalysts, sometimes it will have some degradation of catalyst performance due to agglomeration and other, so here we introduced sulfur confinement effect to improve the catalyst stability. Here is a core shell structure, because we can use nickel iron alloy as the stable support, and we can also have a sulfur nickel sulfide as the catalyst layer. Here we can combine the high activity of the nickel sulfide layer together with the stability of the nickel iron catalyst support. Okay. See, and yeah, we also think about how to combine the activity and the stability one time. Is it possible to realize? Very simple. So here we also invented a reverse method, because usually the high valence state metal can have show high activity, but on the other hand, it will have some stability problem. But if we construct a moderate low valency metal, it will be stable. Under this, based on this consideration, we can try to stretch the bond between metal and oxide, and the stretching effect will increase the activity. In this case, we can combine both activity and stability. And this, I just think about one saying that, okay, distance makes the heart grow fonder. Do I say correctly? In Chinese, is different. Okay, so a little bit stretching means a little bit distance, right? And this kind of distance design improves the activity. Okay, so we can get a perfectly the stability from more than 1,000 hours operation at 5 amperes square centimeter very recently. And this slide shows the three-dimensional anode design, because when they fabricate the catalyst into membrane electrode assembly, the catalyst particles tends to face a problem, the mass transfer limitation. So if we develop a three-dimensional anode, then we can get a better mass transfer property. Here we set up a platform to evaluate the visually, visual investigation for anion exchange membrane water electrolyzer. We can get through the three-dimensional design. We can get a smaller bubble appeared in the MEA. Okay. Next is for hydrogen evolution. I think the concept is similar with oxygen evolution reaction. This is the calculation, mathematical calculation for screening which kind of a structure or composition will show good performance. Here, after calculation, we select nickel ruthenium oxide alloy should have a potential as promising candidates for hydrogen evolution in cathode. Okay, and this we based on the calculation, we did some experiments using one-pot hydrothermal process and followed by the calcination at 350 degrees C, and we can get some information from the high resolution images that the nickel catalyst is uniformly distributed on the catalyst surface. You can see some, especially the yellow circles is the defective site, which induces the high activity. And this slide is also the calculation method. How does nickel influence the ruthenium oxide as a catalyst for an water electrolyzer? And if you want to get some more detailed information, you can look at our the paper, because it's a long story. I cannot say. Okay. Angle just last year we published this paper, and this kind of also the same for HER development for the catalyst experiments. Can see using the nickel and the ruthenium oxide together with ruthenium metal. Here is a complicated composite alloy. We can get a high performance for water electrolyzer device, and also we get a relative 1,000 hours stability using this kind of catalyst. And another part is for ORR, for fuel cell study, because the catalyst as well as membrane, we need to evaluate the final performance in the device. And for ORR study, we found that the pod design enhances internal oxygen transfer efficiency. That is, porous structure is beneficial to increase the PEM fuel cell performance. And the mass transfer situation will also be increased to some degree. Okay, here we cannot show here this. It's okay, no problem. And also for PEM fuel cell performance investigation using the self-made catalyst for ORR in the cathode. You see, we found that the more massive pores will result in higher site density together with higher iron utilization, the catalyst utilization than precious catalyst development. And here I will show a little bit about the materials performance in the device, such as PEM fuel cell, M fuel cell, or corresponding electrolyzers. Basically, from last 3 years, we did some research about catalyst and ionomer, and we can synthesize more and more, can get then can scale up the catalyst fabrication. And we started the MEA from a relatively small size, for example, 4 square centimeter, and until now we can get around the 600 square centimeter. And through this materials research, we can also get in some information which kind of a gas distribution layer is good to establish a high performance MEA. And basically, when we use our novel materials, we can get some improvement in electrolyzer efficiency, especially in 20 and 23. If we look at the stability of the water electrolyzer, we found it's stable for 400 hours at relatively low current density, such as 0.5 ampere per square centimeter. But last year we can even enlarge the durability of the water electrolyzer. When we use the three-dimensional electrode, and we can get a perfect good stability during the cycle experiment. And we published several papers such as small general material chemistry and advanced functional materials. And you can look at the references. And for PEM fuel cell, when we use our self-made catalyst in ORR, we developed a serious multi-scale evaluation from materials to component and to system device. For example, using RDE test, we can investigate the microscope relationship between the material structure and the performance. Okay, then we can investigate the half cell test using the materials self-made. Then we can investigate the single cell performance. So it is a multi-scale evaluation procedure. Okay. As to MEA, we can here show the catalyst layer, the porous structure, how porous structure affect the MEA performance. We get a fuel cell performance, you see, at about 100 degrees C, we can get a good MEA performance, because this condition is a little bit a challenge. Usually we just pay attention to the low temperature PEM fuel cell performance, for example, lower than 80 degrees C, because higher temperature will result in lower humidity condition and is crucial for fuel cell performance. Okay. And specifically as to the oriented electrolyte membrane, when we investigate the PEM fuel cell and M fuel cell using oriented membrane, we can get obviously improvement compared with the commercially naphthalene or other membrane. For PEM fuel cell at 95 degrees C, using the oriented membrane and naphthalene comparison, you can get 80% increase in fuel cell performance. And for M fuel cell, when we test the fuel cell performance at 80 degree and a lower relative humidity, such as 40%, you can get a much better performance for oriented membrane fuel cell performance. And it also shows good stability of the performance in a harsh condition, 120 degrees C and the low humidity level. Okay. So in summary, I'd like to say that in our group, we start from the materials design and the microscopic research And later we do some study using these materials to fabricate MEA. And the MEA can be used for both fuel cell and water electrolyzer. And we can do some a little bit scale production for both membranes and catalyst, and especially for water electrolyzer. We can produce about 1 standard liter pure hydrogen using the MEA self-made. And thanks to sponsorship in SFC, and we have many cooperation with companies, including Toyota. And okay, this is our group is not large. We have about 10 post PhD students and some master students. And here, this is a form teacher, Michael Geller, Zhi Feng, Lian Xin, and me. So our group is not large. And the last, I want to say something about an advertisement. Yeah, this year in Japan, in Fukuoka, not Fukuoka, Fukuoka, right? Yeah. The World Fuel Cell Conference. If you have some interest, you can go to Fukuoka, Japan to give some talk or attend this conference. And here is the website. See, and I hope you can see you in the conference. Sorry for my poor English. Sometimes I don't know how to distribute. Thank you.
Thank you for listening to the podcast of Loughborough University's Institute of Advanced Studies. A quick reminder about how to stay connected. You can find us on Blue Sky, LinkedIn, and Instagram, and you can also watch the presentations on YouTube. The podcast is available on all the major platforms. Please download, share, and most importantly, subscribe. See you next time.